Hello, this is Nick FV, back with another video. This one I wanted to fix a bug from the previous video where I would run a simulation and basically the truss would explode. Whenever I set these links to have a stiffness factor of 100, and when I ran that, this is the simulation that we would see, which is obviously not ideal. Unless you were trying to do something like this. But the reason that this is happening is actually not because of the stiffness itself. Well, it sort of is, but it's actually this pixel per meter constant that I defined up here. So if you control click on it, it shows where it's being used. And I use it in this line of this calculation. So basically what I'm saying is that I set the position to velocity times the delta t, and then I also multiply this pixel per meter, which makes sense mathematically, but I can show you how it's unstable with some drawings. Before I do that, I'm going to go ahead and set this pixel per meter value back to 1, essentially just canceling it out of the calculation. And if I rerun this, I expect to see a slow simulation, but one that doesn't explode. So we see that, and we might expect this to deflect a little bit more than it did. So I can actually increase this gravitation constant. Maybe I can increase that up by 50. So if I refresh that, I'm essentially running the same simulation that I would have if my pixel per meter was 50 here, but instead I'm applying it at this step of the calculation. So what I'm going to do here is I'm just going to get rid of pixel per meter. So now my simulation runs and I can refresh that and we should see the same simulation again. So let's try increasing the damping by another factor of 10. And this also works. I'm going to show you why it wasn't working to begin with. At the beginning of the simulation, let's say we have a link or a spring of length L0. So I'll draw that here. And after one frame, let's say the spring is under tension, so it is stretched a little bit. So it is stretched by some delta L value, which is the same as x. And so it is experiencing some kind of compressive force. The force exerted by a spring is F equals negative kx, where k is the stiffness and x is the change in length of the spring. But what I was actually doing in the logic was I was multiplying by some extra factor here. So I'll call that P. And basically this number was the pixels per meter value that I chose. And so this force was being multiplied by some extra factor here. So the force was P times as large as it really should have been. So in the next frame, the spring was in compression P times as much as it really should have been. So now it has a force pulling this way that is another P times as much as it should be. So in the following frame, now we have an even more stretched out spring, where you can see now all of these extra factors are adding on top of each other. And so if I were to plot this, so if this is tension and this is compression, we start out in the middle at equilibrium, and with some tiny deviation, we see bigger and bigger dips. Basically, the spring is slowly moving to infinity and becoming unstable. And so that's why we saw the system basically explode. So now that we've removed that pixel per meter value from our globals, we can actually set these stiffness constants to a very high number, and the system will still remain stable. So I hope that explained what was going wrong in the previous video, and I'll see you in the next one. Thanks for watching.